Alright, so welcome to the series on integration techniques. In this particular video, we're going to be looking at integrals of this form, where you basically have some constant plus a constant times x to the power of n. Now, you may have come across the formula for this particular type of integral, but it may not be so obvious that this actually derives basically from the integral of x to the power of n dx. So the main idea behind it is that you know what this integral is, because this is basically the basic integral that you learn in order to do every other integral that you come across. So you know that you can just add 1 to the power, and then you just divide this by n plus 1 plus c. And you can verify that that is the case, because if you differentiate this function, then what you're going to get is you're going to get n plus 1 over here times x n plus 1 minus 1 over n plus 1. The c just becomes 0 when you differentiate it, so basically this term and that term are going to cancel out, so you're left with x to the power of n, and this is the original function that you had here. Now, when we're going to solve this integral, we can actually notice that the same kind of thing happens here. So essentially, what we can do is we can perform a substitution. We can say let some variable u equals to a plus bx. And now from that, what we're going to do is we're going to say, okay, so if we differentiate u with respect to x, we're left with just b times dx. So now what we can do is we can place this in here. So obviously we would want to have a b in front here, so that b times dx gives us du. So what we can do is we can rewrite this integral in the following way. We can put a b here at the front, so a plus bx to the power of n dx. And then in order to balance out the fact that we just included this variable here, we can just divide the outside by b. So now what you do is, well, basically this is the same as multiplying the integral by b over b, which becomes 1. But in this case, now you have the integral in a form that actually resembles what you're actually trying to substitute in here. So the next step in this process is essentially just plugging this back into here. So this is going to go in here. So you have 1 over b of the integral of u to the power of n times du. And now you're just going to perform the integration, but now with respect to the variable u. So you're left with 1 over b times u to the power of n plus 1, just following the essential formula here. And then you're going to divide this by n plus 1. So the n plus 1 is going to be multiplying the b now, and plus some constant c. But now, of course, we were integrating with respect to x first, so in order to bring this back, what you do is you substitute this back into u. So you're going to get a plus bx to the power of n plus 1 over b times n plus 1 plus c, which is the formula that you would have seen in a standard table of integrals. So essentially this is just to show you that it's sometimes better to think of a problem not in terms of the actual formula that might be found in the table, but rather to think about it, how can you solve it using some integration technique. In this case we use substitution. So to that extent, I believe that this is quite useful. Now you might think, well, could I actually get away with doing this kind of thing over and over again? Well, it only works when you have a linear function. The reason for that is that the derivative of this is just a constant, which is what you have here. So if the derivative of the function is a constant, you can usually get away with it, because you can just multiply the function by a constant by balancing the term out on the outside, dividing by that constant. But let's say that I gave you a more general case, like ax squared plus b to some power n. Now, if we were to apply the same formula, you might think, well, maybe I can do that, but you're going to see that this is actually not correct. So you have n plus 1 here. Now, you might think, oh, maybe I just take, well, if you take the derivative of that, we get 2ax times n plus 1 plus c. But the problem is that if you try to differentiate this, you're not going to get the original function, because now you have a function of x in the denominator. So that's going to require application of the quotient rule. And then what you're gonna have is you're gonna get a function that is even more complicated than this instead of just that. So this technique only works for when you have a function that is a to the power x to the power of 1 inside that brackets. But at least for this case, it's quite useful because you can do things like, for example, let's say you have something like the square root of 1 plus x. Well, in that case, all you need to do is you transform this into the following expression. So you have 1 plus x to the power of half. And now you simply use the original formula, and that's going to give you the integral. So this is going to be 1 plus x to the power of half over half times the derivative of this, which is just 1, plus c. So this, now bring the 2 up. This becomes 2 times 1 plus x to a power of half. Actually 3 on 2. Because remember, we need to add 1 to the power, so that becomes 3 on 2. And then this is 3 here, plus the constant c. So that is essentially what you get. So in general, it can be useful for certain cases, but obviously you need to be careful as to exactly what you're integrating. And it's a really good idea to always differentiate your final function to see that you're getting the right answer.